You know what this T-junction does for whatever's in the pipes connected to it. It can take material from one of its openings and send it in two different directions. This is a similar tool, but for electricity rather than fluids. You plug it into the wall and the mains AC power shows up at all its outlets. You may even have something like this in your home if you have multiple TVs connected to your cable service, or a single TV and a cable modem that both need to use the services provided by a single coaxial cable. Given what I just said, since I work in broadcasting, it would follow that this heavy thing is just a supersized version of the tiny one, right? Well, we do use a lot more power, so it makes sense that the equipment would need to be able to handle it. If you hesitated while considering the question because you've seen my videos before and know there's something special about the heavy thing because I don't do boring show and tell, that would have been the right move. This isn't a ho-hum RF splitter like what you'd have in your home to put two things on one line. This is a specialized device called a circulator.
An RF circulator does just what its name suggests. It circulates radio frequency signals among its ports. Here's the schematic symbol for a circulator overlaid for reference. You'll notice that the ports on most circulators are numbered. This one has small labels designating ports 1, 2, and 3. An RF signal entering any of the ports of a circulator will only exit from the next port, so RF coming into port 1 will only exit port 2. Anything into port 2 will exit port 3, and anything into port 3 will exit port 1. Circulators on their own have two primary uses. In a system where there are separate transmitters and receivers sharing a common antenna, you can use a circulator as a duplexer. With the transmitter connected to port 1, the antenna to port 2, and the receiver to port 3, any output from your transmitter would be sent to the antenna, and anything received through the antenna would go to the receiver. Circulators can also be used as RF isolators. In this setup, there would still be a transmitter connected to port 1 and an antenna on port 2, but port 3 would go to a matched resistive load. In broadcasting, this is what you'll find most circulators used for. Antenna systems are typically custom-built and very well matched for the one frequency used at a particular radio station, but the long runs of transmission line and the antennas themselves are almost always out in the elements, and anything from ice buildup to rain to even the humidity can affect the tuning of the antenna, causing some of the RF power to be reflected back toward the transmitter. With a circulator, this reflected power can be sent to a dummy load where it can safely be dissipated as heat, rather than directly to the transmitter, which may not be able to handle it without being damaged.
Circulators can also be used as components in larger RF systems such as combiners, where they're frequently used as isolators on the input side of bandpass filters. The filtering reduces the amount of RF coming back from the system due to the use of a broadband yet not perfectly matched antenna, but doesn't completely eliminate it. Therefore, circulators are still needed as isolators, but the dummy load on the third port can be smaller. What sort of straight-up wizardry makes something like this work? Your clue might lie in how absolutely heavy this thing is. There are huge magnets inside. That's right, the favorite mystery of Violent J and Shaggy 2-Dope makes an appearance right here in a completely passive device. All three ports connect to a special type of transmission line called strip line, which is like a flat coaxial cable in a dielectric substrate, sort of like a circuit board, where they meet in the center at 120-degree angles to each other. This strip line layer is jammed in between two discs of ferrite material, which itself is sandwiched between powerful permanent magnets. When an RF signal is sent into the circulator on one of its ports, the electromagnetic field inside the strip line interacts with the magnetic field from the permanent magnets, which causes a unique thing to happen. The RF energy splits in two different directions along the circulator's junction, as would happen if there were no magnets involved, but the phase propagation velocity is altered by the external magnetic field depending on the direction of the split. This is called the Faraday Effect, named after Michael Faraday, whose cage you may already be familiar with. This works out to the waves meeting at the next port in the forward direction in phase, where they combine to produce the input signal unmodified. But when they meet at the port in the reverse direction, they are 180 degrees out of phase and combine to cancel to zero, or very near zero. Nothing's perfect. Simple devices like this are small but important building blocks in RF transmission systems, and knowing what they do and how you can use them are important skills in a broadcast engineering career. As we explore the RF side of broadcasting, I'm sure you'll see circulators pop up again. Until then, if you have an interest in learning more about broadcasting and its relation to nerdy topics like electronics and IT, make sure you subscribe and ring the notification bell so you don't miss more stuff like this from me. You can visit my landing page at broadcastblueprint.com. I'll catch you next time.